Look up at the night sky. What do you see? A scattering of stars, perhaps a planet or two, and the vast, empty blackness stretching beyond. But what if I told you that emptiness is an illusion? That hidden in the fabric of space itself are structures so colossal, they make galaxies look like specks of dust. We're talking about cosmic giants, colossal walls of galaxies, unfathomably massive voids, and filaments of matter stretching across billions of light years. These are the largest structures in the universe, and their scale is so mind-bending. It challenges everything we think we know about space, time, and reality itself. Picture this, a single structure so vast it could contain thousands of galaxies, all moving together in an intricate dance across the cosmos. Now imagine that structure is just one thread in an even grander tapestry, a web of galaxies and dark matter that spans the entire observable universe. These aren't just abstract ideas, they're real, measurable phenomena that astronomers have mapped, studied, and marveled at for decades. And yet, despite their staggering size, most people have never even heard of them. That's about to change. Over the next few minutes, we're going to take a journey, a voyage across the cosmos to explore 30 astonishing facts about these celestial titans. We'll uncover how they form, why they defy our understanding of physics, and what they reveal about the very nature of existence. From the mind-blowing Great Wall of galaxies to the eerie cosmic voids where almost nothing exists, each fact will pull you deeper into the mystery and majesty of the universe's grandest designs. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The universe isn't just a random collection of galaxies drifting in isolation. It's a meticulously organized masterpiece woven together by an invisible cosmic architecture. Think of it like a spider's web, but on a scale so vast it's almost impossible to comprehend. This is the cosmic web, the scaffolding of the universe itself. Imagine taking every galaxy you've ever seen in a telescope, every swirling spiral, every glowing elliptical, and realizing they're not scattered haphazardly. Instead, they're strung along immense filaments of dark matter, like glittering beads on an endless, invisible string. These filaments stretch across billions of light years, connecting galaxy clusters in a delicate, intricate dance. But here's where it gets even more fascinating. Between these glowing threads lie vast, empty regions, cosmic voids so enormous they could swallow thousands of Milky Ways without a trace. It's as if the universe built itself with a blueprint, concentrating matter along these tangled highways, while leaving unimaginable stretches of nothingness in between. Scientists believe dark matter, that mysterious, invisible substance that makes up most of the universe's mass, acts like the framework for this web. Its gravity pulls ordinary matter, stars, gas, and galaxies into those dense filaments, creating the dazzling patterns we observe today. And when we say vast, we mean it. Some of these filaments are so long, light would take 10 billion years to travel from one end to the other. Wrap your mind around that. A single structure so colossal, it's older than our solar system, older than Earth itself. The cosmic web isn't just a feature of the universe, it is the universe, the underlying skeleton that shapes everything we see. And yet, for something so fundamental, we've only just begun to map its full expanse. Every new telescope, every deep space survey peels back another layer, revealing just how much we still have to learn about this breathtaking celestial tapestry. As we follow the threads of the cosmic web, we stumble upon something that shouldn't exist, a structure so enormous it defies the very laws of the universe as we understand them. Meet the Hercules-Corona Borealis Great Wall, a galactic megastructure spanning an almost incomprehensible 10 billion light years. To put that into perspective, if you could travel at the speed of light, it would take you longer to cross this single wall than the current age of the universe itself. That's not just big, it's cosmologically outrageous. Scientists first detected this behemoth not by spotting galaxies or clusters, but by mapping something far more violent: gamma-ray bursts. These intense flashes of energy, the universe's most powerful explosions, act like cosmic breadcrumbs. Where they cluster, so too does matter. When researchers noticed an unusual concentration of these bursts in the constellations Hercules and Corona Borealis, they knew they'd found something extraordinary. What emerged from the data was a sprawling, sheet-like structure packed with galaxies, stretching across a tenth of the observable universe. But here's the real shocker: this shouldn't be possible. According to the cosmological principle, a cornerstone of modern astronomy, matter should be evenly distributed on the largest scales. The universe, in other words, ought to look roughly the same no matter where you're observing it from. Yet the Hercules-Corona Borealis Great Wall throws that idea into question. How could such a massive, lopsided structure form? Some physicists suggest it might be a flaw in our observations, a trick of perspective where unrelated bursts appear connected. Others wonder if we're seeing evidence of exotic physics, cosmic strings, alternate dimensions, or forces we don't yet understand. What's undeniable is this: if the Great Wall is real, it forces us to rethink everything from the Big Bang to the fate of the cosmos. Structures this vast shouldn't have had enough time to assemble after the universe's birth. Their existence hints at mysteries lurking in the darkness, secrets written in gamma rays and gravity, waiting to rewrite the story of existence itself. Before the Hercules-Corona Borealis Great Wall shattered our cosmic scale, another titan claimed the title of largest known structure, the Sloan Great Wall. Discovered in 2003, this staggering chain of galaxies spans 1.4 billion light-years, a distance so immense it would take light 1,400 million years just to travel from one end to the other. Picture a string of pearls, each pearl not a single jewel but an entire galaxy cluster, and you're beginning to grasp the sheer enormity of this cosmic behemoth. The story of its discovery is just as fascinating as the structure itself. Unlike spotting a bright star or a nearby galaxy, finding something this vast required mapping the universe in 3 dimensions, a task only possible with the Sloan Digital Sky Survey. This ambitious project used a dedicated telescope in New Mexico to capture detailed images of millions of galaxies, measuring their light to calculate distances. By stitching together these observations, astronomers created the largest 3-dimensional map of the universe at the time. And there, hidden in the data, was the Sloan Great Wall, a galactic filament so enormous it rewrote our understanding of cosmic architecture. What makes this wall so remarkable isn't just its size, but what it reveals about how the universe organizes itself. Unlike random scattering, galaxies here are clustered in a distinct ribbon-like formation, stretching across the constellations Leo and Virgo. Scientists believe such structures emerge from tiny density fluctuations in the early universe, ripples from the Big Bang that grew over billions of years as gravity pulled matter into these intricate, large-scale patterns. Yet even with that explanation, the Sloan Great Wall presents puzzles. Its size pushes the limits of what cosmological models predict should exist, challenging theories about how quickly matter could clump together after the universe's birth. And here's something truly humbling: this wall isn't an isolated anomaly. It's part of an even grander arrangement, linked to other filaments and clusters in the cosmic web. When we peer deep into space, we're not just seeing individual galaxies, but the fingerprints of gravity's patient work across eons, weaving matter into structures that dwarf our entire local galactic neighborhood. The Sloan Great Wall may have lost its largest crown, but it remains a breathtaking reminder of how much more there is to discover in the dark vastness between the stars. Just when we thought we'd seen the limits of cosmic scale, the universe reveals another marvel: the Bootes Great Wall, a staggering filament of galaxies stretching over 1 billion light-years. Discovered in 2016, this galactic leviathan gets its name from the Baryon Oscillation Spectroscopic Survey, or BOSS, an ambitious project designed to map the universe in unprecedented detail. Unlike the Sloan Great Wall's thread-like structure, this titan resembles a sprawling, interconnected network of superclusters, forming one of the most massive known arrangements of matter in existence. What makes this discovery so groundbreaking isn't just its size, but what it tells us about the invisible forces shaping our universe. The BOSS survey wasn't simply counting galaxies, it was hunting for echoes of the early cosmos. By measuring subtle patterns in how galaxies are spaced, scientists could trace the fingerprints of baryon acoustic oscillations, ripples left over from the primordial universe. These cosmic echoes act like a ruler, helping astronomers measure distances and the influence of dark energy, that mysterious force accelerating the universe's expansion. The BOSS Great Wall emerged from this data like a ghostly silhouette, revealing how dark energy and gravity have been locked in a tug of war across billions of years. Here's where it gets even more intriguing. Unlike previous walls, this structure isn't just a passive relic. It's a dynamic arena where dark energy's effects are written into the very arrangement of galaxies. Some researchers suggest its vast, web-like shape might hold clues about why the universe's expansion is speeding up. Could the distribution of matter in walls like these be subtly influenced by dark energy's push, or do they reveal gaps in our understanding of gravity itself? The answers might lie in future surveys, but one thing is certain: the BOSS Great Wall isn't just a curiosity. It's a cosmic laboratory offering front-row seats to some of the universe's deepest mysteries. And yet, for all its grandeur, this wall is likely just one thread in an even grander tapestry. As telescopes grow more powerful, we're realizing these structures aren't anomalies. They're the universe's default setting, woven into existence by the interplay of dark matter, gravity, and dark energy. The BOSS Great Wall doesn't just challenge our measurements, it challenges our imagination, forcing us to grapple with scales and forces so vast, they redefine what we thought possible. Hidden behind the Milky Way's glowing disk, in a region astronomers call the Zone of Avoidance, lies one of the most colossal cosmic structures ever mapped: the South Pole Wall. Stretching a staggering 1.4 billion light-years across, this monumental arrangement of galaxies remained invisible to telescopes for decades, obscured by our own galaxy's dust, gas, and blinding starlight. Its discovery in 2020 wasn't just a triumph of technology, it was a reminder of how much of the universe still hides in plain sight. So how do you find something lurking behind an impenetrable cosmic curtain? The answer lies in gravity's subtle tug. Instead of relying on traditional light-based observations, scientists turned to a clever workaround: measuring the motions of galaxies we can see to infer the presence of hidden giants. Every galaxy moves not just from the universe's expansion, but also in response to nearby gravitational forces. By meticulously tracking these deviations, researchers pieced together the invisible mass pulling on them, revealing the South Pole Wall's silhouette like a shadow cast across the cosmos. What emerged from the data was breathtaking: a vast, curving sheet of galaxies, dwarfing even the Sloan Great Wall in sheer scale. Picture a cosmic tsunami frozen in time, a ripple of matter arcing across the southern celestial sphere. But here's the twist: unlike other great walls, this structure isn't just a distant curiosity. It's surprisingly close, cosmically speaking, with its gravity influencing galaxies in our own intergalactic neighborhood. That proximity raises tantalizing questions. Could this wall's pull explain peculiar motions observed in the Milky Way and Andromeda? Might it reshape our understanding of local galactic flows? The discovery also highlights an irony of cosmic exploration. Sometimes the biggest things are the hardest to see. While telescopes peer billions of light-years into the distance, entire megastructures evade detection simply because they lie behind our galaxy's crowded midplane. The South Pole Wall reminds us that the universe still holds secrets in its blind spots, and with every breakthrough, we're not just mapping hidden structures but rewriting the story of our own place within them. In the vast cosmic dance of galaxies and superclusters, few discoveries have sparked as much intrigue as the giant arc, a graceful, crescent-shaped arrangement of galaxies spanning 3.3 billion light-years. Imagine a structure so colossal it could loop around our observable universe dozens of times over, yet so perfectly curved it seems sculpted by an unseen hand. This staggering formation, uncovered in 2021, isn't just another entry in the catalogue of cosmic giants. It's a riddle wrapped in starlight, challenging our assumptions about how the universe organizes itself on the grandest scales. What makes the giant arc truly extraordinary isn't just its size but its symmetry. Unlike the tangled filaments of the cosmic web or the sprawling sheets of great walls, this structure arcs across the cosmos with an almost artistic precision. Astronomers detected it while mapping the distant universe in the constellation Bootes, using the light of quasars' brilliant beacons from active galactic nuclei to trace the positions of galaxies. As the data piled up, a pattern emerged. Dozens of galaxy clusters, galactic groups, and solitary galaxies all aligned along a curve so vast it defies conventional explanations. The problem, according to our current understanding of cosmology, structures this large, and this coherent shouldn't exist. The universe's matter is thought to distribute randomly on the largest scales, governed by the subtle ripples of the Big Bang and the relentless pull of gravity. But the giant arc's graceful symmetry suggests something else, a level of organization that existing models struggle to explain. Some researchers speculate it could be a remnant of primordial sound waves from the universe's infancy, frozen in time and stretched to unimaginable proportions by cosmic expansion. Others wonder if we're seeing evidence of exotic physics, cosmic strings, defects in space-time, or even flaws in our own theories about gravity and dark matter. Here's where the mystery deepens. The giant arc isn't just a static relic, it's a dynamic puzzle piece in the larger cosmic web. Its curvature aligns eerily with other known megastructures, hinting at connections we've yet to fully unravel. Could it be part of an even grander pattern, a hidden geometry woven into the fabric of the universe? Or is it a statistical fluke, a chance alignment that only appears significant from our vantage point? The questions outnumber the answers, but one thing is certain. The giant arc forces us to confront just how little we truly understand about the universe's largest designs. And perhaps that's the most humbling realization of all. For all our telescopes and supercomputers, the cosmos still holds surprises that upend our expectations. The giant arc isn't merely a curiosity, it's a cosmic whisper, urging us to look deeper, question harder, and rethink the very foundations of what we know. As astronomers continue to probe its secrets, one truth becomes clear. The universe's grandest structures aren't just awe-inspiring, they're masterclasses in humility, reminding us that every discovery is just the beginning of a much larger story. We often think of our Milky Way as an island in space, drifting alone through the cosmic dark. But zoom out far enough, and you'll see it's just one leaf in a vast, swirling forest. Welcome to the Laniakea Supercluster, a sprawling continent of galaxies 520 million light-years across, where 100,000 galaxies move together in a gravitational river, all flowing toward a mysterious, invisible point in space. The name Laniakea comes from the Hawaiian words for immeasurable heaven, and it's a fitting title. Picture this: galaxies aren't scattered randomly but are drawn into colossal superclusters, the largest gravitationally bound structures in the universe. Laniakea is ours, a cosmic watershed where the Milky Way, Andromeda, and every galaxy in our neighborhood are caught in a slow, inevitable drift toward a gravitational anchor known as the Great Attractor. This unseen behemoth, hidden behind the dust of our own galaxy, pulls on everything around it like a celestial whirlpool. Here's what makes Laniakea so extraordinary: it's not defined by visible boundaries but by motion. Astronomers mapped it not by tracing starlight but by tracking the subtle movements of galaxies over decades. Just as rivers flow toward the ocean, galaxies stream along invisible filaments toward denser regions of space. These flows reveal the supercluster's true shape, a web of galactic tributaries converging in a vast, luminous core near the Norma cluster. Yet even Laniakea isn't the end of the story. It's just one branch in an even larger structure, tangled with neighboring superclusters like Shapley and Hercules. Together, they form a hierarchy of scales so vast, our local group of galaxies feels microscopic. And nestled within it all is an unsettling truth: we're not just observers of this cosmic dance. We're participants carried along by forces older than time, part of a story written in gravity and motion. The discovery of Laniakea didn't just redefine our address in the universe, it shattered the illusion of cosmic solitude, those twinkling stars we see at night. They're neighbors in a metropolis of galaxies, all swept up in the same silent tide. And as we peer deeper, we're left to wonder, what other invisible currents shape the cosmos, and where, ultimately, are they taking us? If Laniakea rewrote our cosmic address, the Pisces-Cetus supercluster complex erases the map entirely, revealing a structure so vast it makes superclusters look like neighborhoods. Imagine a cosmic metropolis where Laniakea, Shapley, and other galactic giants are just districts in a sprawling megalopolis stretching 1 billion light-years across. This is the universe's true scaffolding, a web of superclusters containing millions of galaxies, all bound by gravity's invisible threads. What makes this complex so extraordinary isn't just its scale, but how it reshapes our understanding of cosmic hierarchy. For decades, astronomers assumed superclusters were the pinnacle of large-scale structure until they peered deeper and realized these titans themselves cluster together, forming filaments in an even grander design. Picture a Russian nesting doll where each layer reveals a new level of immensity. At the heart of this complex lies the Pisces-Cetus filament, a ribbon of galaxies threading through the constellations it's named after, linking superclusters like beads on a string. Here's where the story takes a fascinating turn. Unlike Laniakea, which was mapped by tracking galactic motions, the Pisces-Cetus complex emerged from painstaking surveys of galaxy redshifts, measuring how much the universe's expansion stretches their light. By analyzing these subtle shifts, astronomers could reconstruct the three-dimensional architecture of space, uncovering patterns invisible to traditional telescopes. The data revealed something astonishing. Superclusters aren't isolated islands, but nodes in a continuous, lattice-like structure, with the Pisces-Cetus filament acting as a backbone connecting them. But the real mystery lies in what this means for cosmology. Current theories suggest such colossal formations shouldn't exist. Their sheer size challenges models of how quickly gravity could assemble matter after the Big Bang. Some researchers propose they're remnants of ancient sound waves from the universe's infancy, frozen in time and stretched to impossible scales by cosmic expansion. Others wonder if dark energy, the force accelerating the universe's growth, plays a role in sculpting these megastructures. And then there's the unsettling possibility that we're still not seeing the full picture. The Pisces-Cetus complex might itself be part of something even larger, a hint that the universe's true structure operates on scales we're only beginning to fathom. Every time we push the boundaries of observation, the cosmos responds by revealing another layer of complexity, another tier of grandeur. This is the humbling lesson of the Pisces-Cetus complex. No matter how vast our tools let us see, the universe always has a way of making us feel small. It's a reminder that the night sky isn't just a curtain of stars, but a living, evolving tapestry, one where every thread connects to something deeper, older, and more magnificent than we'll ever fully grasp. Somewhere beyond the Milky Way's glittering veil, a cosmic enigma lurks, an invisible force so powerful it's dragging entire galaxies toward it at 14 million miles per hour. This is the Great Attractor, a gravitational anomaly that's been bending the paths of stars and galaxies for billions of years, and yet we've never actually seen it. Hidden behind thick curtains of dust and stars in the constellation Norma, this mysterious region defies observation, making it one of the universe's most tantalizing puzzles. Think of gravity as the universe's invisible puppet strings, gently tugging everything from planets to galaxies into motion. Normally, these forces balance out, but the Great Attractor is different. It behaves like a cosmic whirlpool, pulling thousands of galaxies, including our own Milky Way, into its grasp. Discovered in the 1970s when astronomers noticed galaxies in our local cluster weren't just drifting apart with the universe's expansion, but were also being dragged sideways. This anomaly sent shockwaves through the scientific community. Suddenly, the Milky Way wasn't just floating, it was racing toward something unseen, something colossal. But here's where the mystery deepens. When astronomers pointed their telescopes toward the Great Attractor's supposed location, they found almost nothing. The region is obscured by the Milky Way's own galactic plane, a zone so packed with gas, dust, and stars that it's like trying to spot a lighthouse through a sandstorm. What little we've glimpsed suggests a dense concentration of galaxy clusters, like the Norma cluster, but their combined gravity doesn't fully explain the attractor's monstrous pull. So what's really there? Some theories propose a supermassive cluster of dark matter, an unseen halo of mysterious particles exerting far more gravitational influence than visible matter could account for. Others suggest the Great Attractor might not be a single object but part of something even larger, like the Shapley Supercluster, a staggering collection of galaxies 650 million light-years away. Imagine a mountain so vast its foothills are mistaken for the peak. That might be the case here, or perhaps we're seeing the ripple effects of a primordial flaw in space-time, a kink left over from the universe's birth. What's certain is this: the Great Attractor isn't just pulling galaxies, it's pulling our understanding of the cosmos into uncharted territory. Every new observation peels back another layer of the mystery, revealing how much we still don't know about the forces sculpting the universe. And as we strain to see through the Milky Way's dusty blindfold, one question lingers: what other invisible giants are out there, silently steering the fate of everything around them? 650 million light-years from Earth, hidden in the constellation Centaurus, lies the Shapley Supercluster, a gravitational titan so massive, its pull reshapes the motion of galaxies across the universe. Imagine a city of light containing tens of thousands of galaxies, each with billions of stars, all clustered together in a space so dense, it bends the very fabric of space-time around it. This isn't just another supercluster, it's the most massive concentration of matter in our cosmic neighborhood, and its gravity might hold the key to explaining the Great Attractor's mysterious tug. Discovered in the 1930s by American astronomer Harlow Shapley, this colossal structure initially appeared as a suspiciously high density of galaxies in photographic plates. But it wasn't until the 1980s that astronomers grasped its true scale. Modern surveys reveal a staggering truth: the Shapley Supercluster isn't a single entity but a sprawling metropolis of at least 25 galaxy clusters, all bound together in a gravitational embrace. Picture the densest parts of Laniakea, then multiply that by 100. This is the sheer, overwhelming concentration of matter we're dealing with. What makes Shapley truly extraordinary is its role in the cosmic tug-of-war. While the Great Attractor pulls nearby galaxies, including our Milky Way, Shapley's immense gravity acts like an anchor from the opposite direction. Scientists now believe these two giants are locked in a silent battle, with Shapley's overwhelming mass potentially explaining why the Great Attractor's pull seems stronger than visible matter can account for. It's as if we're caught between two cosmic magnets, with Shapley's sheer weight tilting the balance. Yet for all its might, Shapley remains full of puzzles. Its core, the Shapley concentration, glows with the heat of colliding galaxy clusters, so violent they create shockwaves visible in X-ray telescopes. Some researchers speculate that dark matter, that elusive, invisible substance making up most of the universe's mass, could be clustered here in unprecedented quantities, amplifying the supercluster's gravitational reach. Others wonder if Shapley's extreme density hints at a flaw in our understanding of how matter clumped together after the Big Bang. One thing is certain: this supercluster doesn't just dominate its corner of the cosmos, it influences ours. Every time astronomers map the Milky Way's peculiar motion or trace the flow of nearby galaxies, Shapley's fingerprints appear in the data. It's a reminder that the universe operates on scales far beyond our everyday perception, where invisible forces sculpt the paths of galaxies over billions of years. And as we peer deeper into its mysteries, we're left with a humbling thought sometimes: the most powerful forces in the cosmos are the ones we can't even see. Deep in the constellation Bootes lies one of the universe's most unsettling mysteries, a spherical void so vast and empty, it's been called the Great Nothing. Stretching 330 million light-years across, the Bootes void is a cosmic desert where galaxies are almost non-existent. If our Milky Way were placed at its center, we'd peer into the abyss in every direction and see nearly nothing. Just a handful of isolated galaxies dotting an ocean of darkness, like lone ships lost at sea. What makes this void so bizarre isn't just its size, but how starkly it defies expectations. Most regions of space, even the emptiest cosmic voids, still contain some galaxies, perhaps scattered thinly, but present. The Bootes void, however, holds only 60 known galaxies where there should be thousands. To put that in perspective, a typical region of space its size would host around 2,000 galaxies. The void's emptiness is so extreme, it feels less like a natural structure and more like a deliberate clearing in the cosmic forest. So how did this ghostly bubble form? Theories range from the mundane to the mind-bending. One leading idea suggests it's the result of smaller voids merging over billions of years, like soap bubbles combining into one enormous emptiness. Another proposes that dark energy, the mysterious force accelerating the universe's expansion, might have stretched this region more aggressively, pushing galaxies apart until only silence remained. But the most tantalizing hypothesis, that the void is an imprint of something far stranger, a collision between our universe and another during the chaotic aftermath of the Big Bang. Here's where the mystery deepens. Recent observations reveal that the few galaxies trapped inside the void aren't just randomly scattered, they're oddly aligned along filamentary structures, as if clinging to invisible threads. This hints that even in the deepest emptiness, the cosmic web's influence persists, its gravitational scaffolding too powerful to fully vanish. Some astronomers speculate the void might not be entirely empty after all, that vast reservoirs of dark matter could lurk unseen, their gravity subtly shaping the motion of those lonely galaxies. Yet the Bootes void's greatest lesson might be about perspective. For centuries, we've assumed the universe was roughly uniform, that no single region could deviate so drastically from the norm. But this gaping hole in space forces us to reconsider. It's a reminder that even on scales beyond comprehension, the cosmos still holds surprises, pockets of nothing so vast, they redefine our understanding of what empty truly means. And as we stare into that darkness, we're left to wonder, is the void the exception, or are we the ones living in an unusually crowded corner of existence? In the vast expanse of the cosmos, where galaxy clusters and superclusters dominate the landscape, there exists a place so profoundly empty it leaves even the most seasoned astronomers speechless: the Eridanus supervoid. Spanning an almost unimaginable 1.8 billion light-years, this yawning chasm of darkness isn't just a void, it's a cosmic anomaly so massive, it's left a visible imprint on the oldest light in the universe. That light is the cosmic microwave background, or CMB, the faint afterglow of the Big Bang that permeates every corner of space. Normally, this radiation is remarkably uniform, a near-perfect snapshot of the infant universe's temperature. But in 2004, scientists analyzing data from the Wilkinson microwave anisotropy probe stumbled upon something bizarre, a colossal cold spot in the CMB, centered right over the Eridanus constellation. This region was noticeably cooler than its surroundings, as if the universe itself had left a frozen fingerprint there, the leading theory that the Eridanus supervoid caused it. Here's how it might work. As light from the CMB travels through a void, it loses energy climbing out of the gravitational well created by the absence of matter, an effect called the integrated Sachs-Wolfe effect. The result, a patch of sky that appears slightly colder than it should. But here's the catch: the Eridanus supervoid is so staggeringly large, its sheer size challenges our understanding of how such structures form. According to standard cosmology, voids this vast shouldn't exist. The universe simply hasn't had enough time since the Big Bang to grow something so enormous through natural gravitational evolution. Which brings us to the debates tearing through astrophysics. Some researchers argue the supervoid isn't as empty as it seems, that hidden reservoirs of dark matter might lurk within, subtly shaping its properties. Others propose even wilder ideas, that this void is evidence of a collision with another universe during cosmic inflation, a scar left behind by a long-ago encounter with a parallel reality. Then there are the skeptics who question whether the cold spot and the void are truly linked at all, pointing out that statistical flukes can sometimes mimic profound discoveries. Yet what's undeniable is the sheer weight of mystery the Eridanus supervoid represents. It's not just an absence, it's a cosmic question mark, forcing us to reconsider everything from the nature of dark energy to the very limits of our observational tools. Every new telescope pointed at this enigmatic region peels back another layer, revealing not just the secrets of the void but the boundaries of our own understanding. And perhaps that's the most humbling lesson of all. In a universe teeming with unimaginable scale and complexity, even emptiness holds the power to astonish. The Eridanus supervoid doesn't just challenge our models, it whispers of hidden physics, of forces and phenomena we've yet to dream of. As we stare into that cold, dark expanse, we're reminded that the cosmos still has stories to tell. Stories written not in starlight but in the silent spaces between. Hidden in the faint glow of the cosmic microwave background, the universe's oldest light lies a chilling anomaly that has scientists questioning everything they know about reality. The CMB cold spot isn't just a slightly cooler patch of radiation. It's a staggering 1.8 billion light-year stretch of space where the temperature dips dramatically, as if the universe itself left a frostbitten fingerprint behind. But what could possibly create such a vast, icy imprint? The answer might not just reshape our understanding of cosmology, it might rewrite the rules of existence itself. At first glance, the cold spot seems like it could be explained by something mundane, a cosmic void. After all, when light travels through an underdense region of space, it loses energy climbing out of the weaker gravitational field, creating a cooler signal in the CMB. But here's the catch: the Eridanus supervoid, the most likely candidate, isn't nearly large or empty enough to account for the temperature drop. The numbers don't add up, leaving scientists scrambling for alternatives. Could this be evidence of something far stranger, like a bruise from a collision with another universe? The idea isn't as far-fetched as it sounds. According to some theories of cosmic inflation, our universe isn't alone. It might be one bubble in an endless froth of multiverses, each with its own physics, its own laws. If two of these bubbles brushed against each other in the early moments of creation, the energy released could have left a scar, a region where space-time itself was stretched thin, cooling the radiation passing through it. The cold spot, then, wouldn't just be a curiosity, it'd be a window into realities beyond our own. Skeptics argue there's a simpler explanation: statistical noise, a random fluctuation in the data. But the odds of such a pronounced anomaly appearing by chance are astronomically low, less than 1 in a million. That hasn't stopped researchers from proposing other wild possibilities, like a gargantuan black hole from a previous universe or a defect in the fabric of space-time left over from the Big Bang. Each theory pushes the boundaries of physics, forcing us to confront how little we truly understand about the cosmos. What makes the cold spot so compelling isn't just its mystery, it's the way it challenges us to think bigger. For centuries, we've studied the universe assuming it's all there is. But if that faint, frozen patch in the sky is proof of something beyond our cosmic horizon, it changes everything. It means the questions we've been asking might be too small. The answers, it turns out, could be written in the cold, quiet spaces between the stars waiting for us to look closer. In the grand tapestry of cosmic giants, one colossus stands apart, not just for its size, but for the sheer audacity of its existence. Meet Alcyonius, a galaxy so vast it makes our Milky Way look like a speck of stardust. Discovered in 2022, this behemoth stretches an incomprehensible 16 million light-years from end to end, earning it the title of the largest known single galaxy structure in the universe. What makes Alcyonius so extraordinary isn't just its record-breaking scale, it's how it defies expectations. Most galaxies, even the largest elliptical ones, span a few 100,000 light-years at most. But Alcyonius belongs to a rare class called giant radio galaxies, which shoot out enormous jets of superheated plasma at nearly light speed. These jets, powered by the galaxy's supermassive black hole, create towering lobes of radio-emitting material that stretch far beyond the galaxy itself. In Alcyonius's case, those lobes are so immense they could swallow 20 Milky Ways lined up side by side with room to spare. The discovery came almost by accident. Astronomers were sifting through data from the Low Frequency Array, or LOFAR, a network of radio telescopes across Europe, when they noticed strange, faint tendrils stretching across the void. At first, they assumed it was noise, an artifact of the instruments, but as they pieced together the signal, the truth became undeniable. They'd stumbled upon something unprecedented. Nestled in a relatively quiet corner of space, Alcyonius wasn't just another galaxy. It was a cosmic titan, quietly pumping out radio waves on a scale never before seen. Here's where the mystery deepens. Theories suggest that radio galaxies grow larger in low-density environments, where there's less intergalactic gas to disrupt their jets. Yet Alcyonius's surroundings are surprisingly ordinary. No vast cosmic voids, no extreme conditions. How, then, did its jets stretch so far? Some scientists speculate its central black hole might be unusually stable, channeling energy into those colossal lobes for billions of years without interruption. Others wonder if we're seeing the result of a rare cosmic alignment, where the galaxy's jets found a perfect path through the intergalactic medium, allowing them to expand unchecked. But the most tantalizing question isn't just how Alcyonius grew so large, it's why we haven't found more like it. Is this galaxy a freak accident of nature, or are there others lurking in the darkness, waiting to be discovered? Every time we push the limits of our telescopes, the universe reminds us that the boundaries of what's possible are far wider than we imagined. Alcyonius isn't just a record holder, it's a challenge urging us to rethink what galaxies can be. And perhaps that's the most humbling lesson of all. For all our maps and models, the cosmos still holds giants we've yet to meet. Alcyonius isn't the end of the story. It's a signpost pointing toward discoveries that will stretch our understanding even further. As we peer into the radio static between the stars, who knows what other titans are waiting to be found? At the heart of the Phoenix Cluster, one of the most massive galaxy clusters known, a cosmic drama unfolds unlike anything else in the universe. A 2 million light-year weather system of searing gas sculpted by the whims of a monstrous black hole. Picture a storm so vast it could engulf the entire Milky Way 20 times over, where temperatures swing from millions of degrees to near absolute zero, all driven by the push and pull of gravity and radiation. This isn't just a random celestial event. It's a high-stakes battle between creation and destruction, and it's rewriting our understanding of how galaxies evolve. The story begins with the cluster's unimaginably hot gas halo, a superheated atmosphere reaching hundreds of millions of degrees. Normally, gas this hot should cool over billions of years, collapsing inward to birth new stars in a process called a cooling flow. But here's the twist. In most galaxy clusters, central black holes pump out so much energy that they prevent this cooling, keeping the gas simmering in a state of suspended animation. The Phoenix cluster defies this rule. Its cooling flow isn't just happening, it's operating at breakneck speed, with gas cooling and falling toward the center 5 times faster than in any other known cluster. Now enter the black hole, a cosmic maestro conducting this chaotic symphony. As gas rushes inward, it fuels the supermassive black hole at the cluster's core, triggering violent outbursts of energy. Jets of plasma erupt at nearly light speed, punching through the surrounding gas and creating colossal bubbles in the cluster's atmosphere. These bubbles rise like balloons in molasses, stretching hundreds of thousands of light years before bursting, releasing energy that reheats the gas. The result, a self-regulating cycle where cooling gas falls, feeds the black hole, and triggers eruptions that halt further cooling, a delicate dance between collapse and explosion. But the Phoenix cluster adds another layer to the mystery. Unlike other systems where black holes stifle star formation, this one seems to encourage it. Observations reveal newborn stars flickering to life in the cooled gas, suggesting the black hole's influence isn't purely destructive. It's as if the universe has stumbled upon a loophole, a way to nurture stars even in the presence of a ravenous cosmic giant. Some astronomers speculate this could be a glimpse into the early universe, when massive galaxies formed under similarly extreme conditions. What makes this system so extraordinary isn't just its scale but its contradictions. It shouldn't be possible for gas to cool this rapidly near a black hole, yet the Phoenix cluster defies expectations. It shouldn't foster star formation amid such violence, yet it does. Every observation peels back another layer of complexity, revealing a universe far more dynamic and unpredictable than our textbooks suggested. And as we watch this cosmic weather system churn, we're left with a humbling realization. Even the most powerful forces in the cosmos can't resist the universe's stubborn creativity. Travel 10 billion light-years across the cosmos, and you'll witness the birth of a giant, the spiderweb galaxy protocluster, a swirling nest of galaxies in the process of merging into one of the largest structures the universe will ever produce. Unlike the mature superclusters we see nearby, this chaotic nursery offers a rare glimpse into the universe's adolescence, a time when galaxies collided, merged, and forged the colossal clusters we recognize today. What makes the spiderweb so extraordinary isn't just its distance, it's the frenzied activity frozen in time. At its heart lies a massive central galaxy, surrounded by dozens of smaller galaxies caught in its gravitational web like flies spiraling toward a spider. But this isn't destruction, it's creation. Each collision, each merger pumps gas and stars into the growing core, building a future titan one cosmic crash at a time. Astronomers estimate that by the time this protocluster matures, it could rival the Coma cluster, a behemoth containing thousands of galaxies, but right now, we're seeing it in its raw, formative stage. The real breakthrough came when telescopes like the Atacama Large Millimeter Array peered through the dust shrouding this distant system. Instead of a quiet, orderly scene, they found a storm of star formation. Gas streams between galaxies, igniting bursts of new stars at rates hundreds of times faster than in our Milky Way. Filaments of dark matter thread through the chaos, funneling raw material toward the center. It's as if we're watching the universe's assembly line, where gravity sculpts primordial matter into the grand structures we recognize today. Yet for all its violence, the spiderweb holds a deeper mystery. According to current models, protoclusters this massive shouldn't exist so early in cosmic history. the universe simply hadn't had enough time for gravity to gather so much material. Some scientists speculate that rare overdensities in the early universe patches where matter was inexplicably concentrated acted as seeds for these precocious giants. Others wonder if dark energy played a role, its repulsive force sculpting the cosmic web faster than expected. What's undeniable is the spiderweb's value as a time capsule. By studying its tangled threads, astronomers are piecing together how today's serene galaxy clusters emerged from the turbulence of the young cosmos. Every new observation peels back another layer, revealing how the universe transforms chaos into order, and how even the mightiest structures began as nothing more than whispers in the dark. 13 billion years ago, the universe was just a toddler, barely 2 billion years old, yet already, the seeds of today's cosmic titans were taking shape. Meet the Hyperion Proto-Supercluster, a sprawling, chaotic web of galaxies caught in the act of becoming one of the most massive structures the universe will ever produce. Discovered in 2018, this primordial giant isn't just a relic, it's a time machine offering a rare glimpse into an era when the first superclusters were stitching themselves together from the fabric of the young cosmos. What makes Hyperion so astonishing isn't just its age, it's the sheer audacity of its scale. Even in its infancy, this protocluster contained at least 5,000 galaxies packed into a region over 200 million light-years across. To put that into perspective, if you could teleport to its location today, you'd likely find a mature supercluster rivaling Shapley or Laniakea in size. But back then, Hyperion was a work in progress, a tangle of gas, dark matter, and fledgling galaxies, all gravitating toward a destiny far grander than any single galaxy could achieve alone. Peering at Hyperion is like watching a city rise from the desert. Using the European Southern Observatory's very large telescope, astronomers mapped its structure in 3 dimensions, expecting to find a loose, disorganized swarm of young galaxies. Instead, they uncovered a surprisingly advanced cosmic metropolis. Dense knots of galaxies' future clusters were already forming along intersecting filaments, their gravity drawing in rivers of gas and stars. The most massive of these knots, a precursor to today's galaxy clusters, glowed with the heat of colliding gas clouds, its core likely harboring one of the universe's earliest supermassive black holes. But here's the real mystery: Hyperion shouldn't exist, at least not in this form. Cosmological simulations suggest that structures this massive and organized should have taken billions of years longer to assemble. Some scientists speculate that Hyperion's rapid growth was fueled by an unusually dense patch of dark matter, a cosmic overdensity, left over from the Big Bang that acted like a gravitational magnet, accelerating the clustering process. Others wonder if the rules of galaxy formation were simply different in the early universe, with hotter gas and more frequent collisions enabling faster assembly. Yet Hyperion's greatest gift isn't just the questions it raises, it's the perspective it offers. By studying this ancient blueprint, astronomers can trace how today's serene superclusters emerged from the chaos of the young cosmos. Every filament, every knot of galaxies in Hyperion is a snapshot of a universe learning to build itself, one gravitational handshake at a time. And as we stare deeper into its tangled web, we're reminded that even the mightiest structures began as whispers in the dark, fleeting moments in a story still being written. 4 billion light-years from Earth, hidden among the stars of the constellation Pisces, lies a discovery so vast it rewrote our understanding of the early cosmos, the Saraswati Supercluster. Named after the ancient Sanskrit goddess of wisdom and learning, this celestial titan spans 600 million light-years and contains the mass of 20 quadrillion suns, making it one of the most massive structures ever spotted in the universe's distant reaches. But what makes Saraswati truly extraordinary isn't just its size, it's the shocking era in which it formed, defying everything we thought we knew about how quickly cosmic giants could assemble. When Indian astronomers first detected Saraswati in 2017 using data from the Sloan Digital Sky Survey, they were stunned by its maturity. Here was a fully fledged supercluster, a dense network of galaxy clusters and filaments, already thriving when the universe was just half its current age. According to conventional models, gravity shouldn't have had enough time to pull matter into such an elaborate structure so soon after the Big Bang. It's like finding a skyscraper in the ruins of an ancient civilization that, by all accounts, hadn't yet invented the wheel. The key to Saraswati's existence might lie in its namesake, a river of galaxies. Unlike modern superclusters like Laniakea, which are still actively gathering new members, Saraswati appears frozen in time, a snapshot of a bygone cosmic era when matter flowed along the universe's primordial filaments like water through a riverbed. 43 massive galaxy clusters anchor this sprawling network, each one a metropolis of stars bound together by dark matter's invisible glue. Some researchers speculate that this supercluster was born in a rare, overdense region of the early universe, a cosmic anomaly where matter pooled more densely than average, jump-starting gravity's work ahead of schedule. But the mystery deepens when you examine Saraswati's surroundings. Unlike younger superclusters nestled comfortably within the cosmic web, this ancient giant exists in a puzzling void, a vast, relatively empty region of space where few other large structures reside. How did such a colossal assembly grow so isolated? One theory suggests it might be a relic of the universe's earliest sound waves, when pressure variations from the Big Bang sculpted matter into alternating bands of density. Another proposes that dark energy, the mysterious force accelerating cosmic expansion, played a role by stretching space unevenly, leaving Saraswati stranded like an island in an ever-widening sea. What's undeniable is the supercluster's power to challenge assumptions. By studying its fossilized architecture, astronomers are piecing together a radical new timeline of cosmic evolution. One where titans rose faster, earlier, and in stranger places than anyone predicted. Saraswati isn't just a structure, it's a question carved in starlight, asking us to reconsider when and how the universe learned to build its grandest designs. And as telescopes probe deeper into the past, who knows what other ancient giants are waiting to be found, silent witnesses to a cosmos far more dynamic and far more mysterious than we ever imagined. At the very edge of the observable universe, something impossible is happening. Galaxies are being pulled toward a point we cannot see. This eerie phenomenon, known as dark flow, suggests an unseen force beyond the cosmic horizon is tugging on everything in its grasp. Picture throwing a stone into a still pond and watching ripples spread outward, except in this case, the ripples aren't moving randomly. They're all streaming in the same direction, defying the expected chaos of cosmic expansion. The discovery came from NASA's a Wilkinson microwave anisotropy probe, which mapped the subtle motions of galaxy clusters by studying the cosmic microwave background. Scientists expected to see random movement. After all, the universe's expansion should scatter matter evenly in all directions. Instead, they found hundreds of clusters drifting at breakneck speeds toward the constellations Centaurus and Hydra, as if drawn by some immense invisible attractor. The strangest part, this motion can't be explained by anything within the known universe. Whatever's pulling these galaxies lies beyond our observable horizon, beyond the 18 billion light-year limit imposed by the speed of light since the Big Bang. That raises a staggering possibility. We might be seeing the gravitational influence of another universe. According to some theories of multiverse cosmology, our universe could be one bubble floating in an infinite foam of others, each with its own physics and dimensions. If a neighboring bubble brushed against ours in the distant past, its gravity might still be pulling on our matter, creating this mysterious flow. Skeptics argue it could be a statistical fluke or an error in data interpretation, but the signal persists across multiple studies, growing stronger with each new survey. Yet dark flow isn't just a theoretical curiosity, it's shaking the foundations of cosmology. If confirmed, it would violate the cosmological principle, the bedrock assumption that the universe is uniform on large scales. Suddenly, the cosmos isn't just expanding, it's being stretched in a specific direction by forces we can't observe, can't measure, and don't understand. Some researchers propose even wilder explanations, a gargantuan structure left over from a previous cosmic cycle, or a glitch in spacetime itself where the rules of gravity break down. What makes dark flow so unsettling isn't just the mystery, it's the realization that we might forever lack the tools to solve it. The culprit lies beyond the cosmic horizon, in regions whose light will never reach us. Yet, like sailors spotting distant currents, we can infer its presence by watching how our own universe bends toward the unknown. It's a humbling reminder that for all our maps and models, we're still just beginning to chart the true scale of existence, and that some answers might always lie just out of reach. The Great Wall of Galaxies Hercules-Corona Borealis stretches 10 billion light-years, a structure so vast it shouldn't exist, not just because of its size, but because of its age. According to our best models of cosmic evolution, the universe simply hasn't existed long enough for gravity to assemble something this colossal. Think of it like trying to bake a wedding cake in 5 minutes. No matter how perfect the ingredients, physics imposes limits. Yet here it is, a galactic megastructure defying the cosmic clock. This paradox cuts to the heart of modern cosmology. After the Big Bang, the infant universe was a near-uniform soup of matter and energy. Tiny quantum fluctuations, ripples no larger than subatomic particles slowly amplified by gravity over billions of years, became the seeds for galaxies and clusters. Simulations show this process should create structures no larger than a few 100 million light-years by now. The Great Wall's existence suggests something's missing from that picture. Either gravity worked faster than we thought, or the universe's initial conditions were far more uneven than the cosmic microwave background implies. One radical explanation grips astronomers: inflation's fingerprints, the theory that the universe expanded exponentially in its first fraction of a second might hold the key. If inflation wasn't perfectly uniform, if certain regions stretched faster or slower, it could have created primordial overdensities, patches where matter was already clustered, giving gravity a head start. Imagine blowing up a balloon with thicker and thinner rubber. The thicker spots would naturally bunch up as the balloon expands. Similarly, slight irregularities in inflation might have left behind cosmic breadcrumbs where structures like the Great Wall could form ahead of schedule. Yet even this elegant idea struggles to account for the wall's jaw-dropping scale. Some theorists wonder if dark matter, the invisible scaffolding of the cosmos, behaves differently on these vast scales, clumping faster than models predict. Others flirt with more exotic possibilities. Cosmic strings, hypothetical spacetime defects from the early universe, could have acted as gravitational shortcuts, accelerating structure formation. Or perhaps dark energy, which now drives the universe's expansion, played a role in the past by temporarily weakening gravity's grip, allowing matter to cluster more freely during a critical window. The wall's defiance isn't just a theoretical headache, it's an observational beacon. By studying its galaxy distribution, astronomers hunt for clues in the patterns. Are galaxies arranged in ways that hint at primordial sound waves from the Big Bang? Do their velocities suggest unseen dark matter currents? Each measurement narrows the possibilities, but the wall guards its secrets fiercely. Even its distance is disputed. Some argue its apparent size could be a trick of perspective, with unrelated galaxy clusters lining up by chance. Yet the more data we gather, the more the wall's reality solidifies. What's undeniable is the existential itch it leaves behind. If our models can't explain the Great Wall, what else might they be missing? Every time we push telescopes harder, the universe reveals structures that stretch or snap our understanding of cosmic time. Perhaps the wall isn't an anomaly but a signpost pointing toward a deeper truth about gravity, dark matter, or the very nature of the Big Bang itself. Until we crack its code, one lesson stands clear: the universe writes its own rules and we're still learning to read them. For centuries, astronomers clung to a comforting assumption that on the largest scales, the universe is fundamentally uniform. This idea, known as the cosmological principle, suggests that if you zoom out far enough, say beyond 1 billion light-years, matter should distribute evenly in all directions. No special places, no overwhelming structures, just a cosmic sameness stretching endlessly in every direction. It's a tidy rule, one that anchors our models of cosmic evolution. But the universe, as it turns out, has a habit of defying tidy rules. The Hercules-Corona Borealis Great Wall, the Saraswati Supercluster, the giant arc, these titanic structures don't just push the boundaries of size, they smash through the cosmological principle entirely. Each one spans distances far exceeding that critical 1 billion light-year threshold, yet instead of dissolving into uniformity, they stand out like mountain ranges against a flat horizon. Imagine looking at a sandy beach from a distance and expecting a smooth, even surface, only to discover, upon closer inspection, that some of the sand grains have formed towering sculptures taller than skyscrapers. That's the level of contradiction we're dealing with here. So why does this matter? The cosmological principle isn't just philosophical musing. It's baked into the equations governing everything from the Big Bang to dark energy. Einstein himself relied on this assumption when developing general relativity, treating the universe as a homogeneous fluid for simplicity. Modern cosmology follows suit, using it to interpret the cosmic microwave background and model the universe's expansion. But if these megastructures are real, they force us to confront an unsettling possibility: that our average view of the cosmos might be flawed, or worse, entirely fictional. The implications ripple outward. If matter isn't evenly distributed on the largest scales, it could mean our measurements of dark energy, calculated under the assumption of uniformity, are subtly skewed. Perhaps the universe's expansion isn't accelerating as uniformly as we thought. Or maybe these structures hint at primordial conditions far more violent and uneven than the smooth cosmic microwave background suggests. Some theorists even speculate that we're seeing the fingerprints of an earlier universe, a pre-Big Bang era where matter was already clumped in ways that persist today. Yet not everyone is convinced these structures break the rules. Skeptics argue they might be statistical illusions, temporary alignments of unrelated galaxy clusters that only appear connected from our vantage point. Others suggest the cosmological principle might still hold, just on scales even larger than we've observed. After all, our observable universe is a finite bubble. Could these megastructures be mere threads in a tapestry far grander than we can see? The debate boils down to a single profound question: is the universe truly a place of order and symmetry, or are we fooling ourselves with assumptions that crumble under closer scrutiny? Every time a new telescope peers deeper into the void, it risks uncovering another anomaly, another crack in the foundation of cosmology. And if the principle falls, we'll need more than revised equations. We'll need a whole new way to understand the cosmos, one where even emptiness has structure, and greatness never truly ends. Before Hercules-Corona Borealis or Saraswati, before modern sky surveys mapped the cosmic web in 3 dimensions, there was the CFA2 Great Wall, a discovery so groundbreaking it ripped apart astronomy's playbook overnight. Found in 1989 by a team at the Harvard-Smithsonian Center for Astrophysics, this 700 million light-year thread of galaxies wasn't just large, it was unthinkable, a structure so vast it forced scientists to confront an uncomfortable truth: the universe wasn't the random, evenly distributed expanse we'd assumed. It had architecture. The revelation came from painstaking pencil and paper work, Before digital sky surveys, astronomers mapped galaxies one by one, plotting their positions on paper charts. As the CF survey accumulated data, a pattern emerged: not the expected cosmic static, but a startling ridge of galaxies stretching from Ursa Major to Coma Berenices. Dubbed the Great Wall, it dwarfed anything in existing models. Imagine spending your life believing mountains couldn't grow taller than hills, then suddenly discovering Everest. That was the shock. This wall delivered proof that gravity could sculpt matter on scales previously deemed impossible. What made this structure so revolutionary wasn't just its size, but its defiance of the cosmic lottery. According to prevailing theories, galaxy distribution should resemble a fair dice roll: clusters here and there, but no overwhelming patterns. Yet the CFA2 wall's galaxies weren't just clustered. They were strung together like pearls on a necklace, tracing a curve so pronounced it couldn't be coincidence. Some theorists scrambled to explain it as a chance alignment, but the statistics were brutal. The odds of such a dense, coherent structure forming randomly were less than 1 in 100,000. The wall's legacy lies in what came after. It shattered the myth of cosmic uniformity, spurring telescopes like Sloan and 2DF to map deeper, revealing even larger structures. Yet ironically, the CFA2 wall itself has faded from headlines, not because it shrunk, but because we've since discovered giants that make it look modest. That's like forgetting the Wright Flyer after the 747, but here's what still astonishes. This unassuming thread of galaxies, found with analog tools and sheer persistence, was the first crack in cosmology's foundation. Every great wall discovered since stands on its shoulders a reminder that sometimes the universe's most important truths hide in plain sight, waiting for someone to connect the dots. Deep in the southern skies, hidden among the stars of the constellation Horologium, lies a gravitational empire so vast it bends the very motion of galaxies around it, the Horologium Supercluster. This sprawling metropolis of matter stretches 550 million light-years across, containing more than 5,000 galaxy groups, each one a bustling hub of stellar activity. But what makes Horologium truly remarkable isn't just its sheer size. It's the way this colossal structure acts like a cosmic conductor, orchestrating the movement of galaxies across unimaginable distances. Imagine the universe as a slow-moving river with galaxies drifting along invisible currents. Most of these flows are gentle, shaped by the subtle pull of nearby clusters. Horologium, however, is a gravitational rapid, a concentration of mass so dense, its influence echoes across hundreds of millions of light-years. Astronomers first detected its power not by spotting galaxies but by tracking their peculiar velocities, the subtle deviations from the universe's uniform expansion. Like leaves caught in a whirlpool, galaxies near Horologium are being drawn inward, their paths bending toward this hidden titan in a phenomenon known as large-scale flow. Here's where the story gets even more intriguing. Horologium isn't just pulling galaxies, it's locked in a celestial tug of war with another giant, the Shapley Supercluster. These two behemoths, separated by nearly 1 billion light-years, are the dominant players in our local universe's gravitational field, their competing forces shaping the trajectories of everything in between. Our own Milky Way feels their influence, caught in a slow drift between these cosmic heavyweights. Some researchers believe Horologium's pull might even help explain anomalies in the Milky Way's motion, hints that our galaxy's journey isn't as straightforward as we once thought. Yet for all its might, Horologium remains shrouded in mystery. Unlike Northern Hemisphere structures which benefit from decades of telescope focus, this southern giant has been harder to study, its depths less mapped. Recent surveys, however, are revealing surprises like the supercluster's unusual filamentary arms, which stretch farther and weave more tightly than models predicted. Some filaments appear to bridge Horologium with neighboring structures, suggesting it might be part of an even larger network, a hidden nexus in the cosmic web. What emerges from the data is a portrait of a dynamic, evolving structure, one that challenges assumptions about how superclusters form and grow. Its sheer density hints at an ancient overdensity, a region where matter pooled more thickly in the early universe, giving gravity a head start. But its intricate filaments suggest a more complex history, shaped by collisions, mergers, and dark energy's relentless push. Every new observation peels back another layer, revealing how these giants don't just inhabit the cosmos, they actively shape it, bending the paths of galaxies and rewriting the rules of motion on the grandest scales. And perhaps that's the most humbling lesson horologium offers. We often think of galaxies as isolated islands, drifting alone through the void. But structures like this remind us that nothing in the universe truly moves in isolation, that even across billions of light years, gravity's invisible threads connect us all, weaving a story far larger than we'll ever fully comprehend. As telescopes probe deeper into horologium's secrets, one truth becomes clear. The universe isn't just expanding, it's dancing, and superclusters like this are calling the steps. Tucked within the sprawling expanse of the Coma Supercluster, where thousands of galaxies gather in a gravitational embrace, lies a structure so immense it redefines our sense of scale, the Coma Wall. Stretching 500 million light-years across the constellations Coma Berenices and Virgo, this colossal filament isn't just a random assembly of galaxies, it's a backbone of the cosmic web, a thread of matter woven into the universe's grand design. At its heart pulses the legendary Coma Cluster, a dense metropolis of over 1,000 galaxies, each one a swirling island of stars bound together by dark matter's invisible grip. What sets the Coma Wall apart isn't just its size, it's the sheer density of its celestial inhabitants. While other great walls span vast distances with galaxies scattered thinly, the Coma region packs them in like skyscrapers in a downtown core. The Coma Cluster alone is a gravitational powerhouse, its combined mass bending spacetime so fiercely that it acts like a lens, distorting the light of galaxies far behind it, a phenomenon called gravitational lensing. But the cluster is just the brightest jewel in a much larger crown. Surrounding it are sprawling galaxy groups and smaller clusters, all strung along the wall's filamentary structure like beads on a cosmic necklace. The wall's discovery in the late 20th century came as a revelation. Astronomers had long studied the Coma Cluster, but it wasn't until wide-field surveys mapped the region in 3 dimensions that the full scale of its surroundings came into focus. Suddenly, what appeared as isolated clusters revealed themselves as nodes in a vast network, connected by tendrils of galaxies and dark matter. This wasn't just a cluster, it was a celestial megalopolis with the Coma Cluster as its bustling downtown and smaller groups as suburbs, all linked by highways of gas and stars. Yet the Coma Wall harbors mysteries that challenge our understanding of cosmic evolution. Its galaxies move at speeds too fast for the visible matter to hold them together, a telltale sign of dark matter's dominance. Even more puzzling is the missing satellite problem. Simulations predict the cluster should host thousands of dwarf galaxies orbiting like moons around a planet, yet observations find far fewer. Some researchers speculate these missing dwarfs were torn apart by tidal forces, their stars scattered into the cluster's diffuse halo. Others wonder if dark matter behaves differently in such extreme environments, clumping less efficiently than models suggest. The wall's influence extends far beyond its immediate neighborhood. Like a boulder in a stream, its immense gravity deflects the motion of galaxies millions of light-years away, contributing to the mysterious, large-scale flows that ripple through our cosmic neighborhood. Some of these flows even tug subtly on our own Milky Way, a reminder that no galaxy, no matter how isolated it seems, is ever truly alone. But perhaps the Coma Wall's greatest lesson is about time. Unlike the fleeting structures of the early universe, this colossal filament has endured for billions of years, its galaxies slowly merging and evolving in a dance dictated by gravity. It's a living fossil, a snapshot of how the universe builds and sustains its grandest designs, and as telescopes peer deeper into its depths, they're uncovering not just answers but new questions about dark matter, galaxy formation, and the invisible forces that bind the cosmos together. In the end, the Corona Wall isn't just a structure, it's a mirror. It reflects our own place in the universe, not as isolated observers but as participants in a story written in gravity and motion, one where even the mightiest walls are just threads in a tapestry far grander than we can see. Stretching across the northern skies like a celestial serpent, the Perseus-Pisces Supercluster winds its way through the constellations. It's named after a sprawling network of galaxies that forms one of the most prominent filaments in our cosmic neighborhood. This isn't just a random assortment of stars and clusters. It's a gravitational masterpiece, a thread in the universe's grand tapestry that links thousands of galaxies across 650 million light-years. But what makes Perseus-Pisces truly extraordinary isn't its size alone. It's the role it plays as a cosmic bridge, connecting even larger structures in a hidden architecture we're only beginning to map. At the heart of this supercluster lies the Perseus cluster, a gravitational titan whose black hole pumps out sound waves so powerful they've been dubbed the deepest note in the universe, a B-flat 57 octaves below middle C, reverberating for millions of years. Surrounding it are galaxies caught in a slow-motion dance, their orbits dictated by dark matter's invisible pull. Yet Perseus cluster is just one luminous node in a chain that stretches farther than the eye can see. Trace its path and you'll find it merging with the Pisces cluster, another dense hub of galaxies, creating a continuous filament that arcs across the void. Here's where the story takes a fascinating turn. Perseus-Pisces isn't an isolated structure. It's part of something even grander. Recent surveys suggest it may link to the larger Pisces-Cetus supercluster complex, forming a segment of one of the longest filaments in the observable universe. Imagine a highway system where galaxies are cities, and dark matter acts as the roads guiding their motion. Perseus-Pisces is one of the busiest interchanges, funneling matter and energy across unfathomable distances. But the supercluster holds mysteries that challenge our understanding of cosmic evolution. Unlike other massive structures, which tend to align with the cosmic web's expected grid-like pattern, Perseus-Pisces curves in ways that simulations struggle to replicate. Some astronomers speculate this could be evidence of ancient tidal forces, gravitational imprints from long-ago collisions with other superclusters. Others wonder if dark energy, the mysterious force accelerating the universe's expansion, might be subtly warping the filament's shape over time. What's undeniable is the perspective Perseus-Pisces offers. By studying its galaxy's motions, astronomers have uncovered clues about the universe's hidden scaffolding, the dark matter framework that dictates where and how galaxies form. Its sheer scale also serves as a reminder of our own place in the cosmos. The Milky Way sits on the outskirts of this colossal structure, a tiny suburb in a sprawling galactic metropolis. And as telescopes peer deeper into its depths, they're not just mapping a supercluster, they're unraveling the story of how gravity sculpts the universe, one filament at a time. Buried within the Ophiuchus supercluster, nearly 400 million light-years away, lies evidence of a cataclysm so violent it dwarfs every explosion since the dawn of time. In 2020, astronomers uncovered a cavity in space 15 million light-years wide, a gaping hole in the cosmic fabric so immense it could swallow 15 Milky Ways side by side without touching the edges. This isn't just a void, it's the scar of a detonation 5 times more powerful than the previous record holder, a black hole's tantrum so colossal, it rewrote our understanding of cosmic violence. The eruption's source, a supermassive black hole at the cluster's heart, but not in its active feeding phase. Instead, this behemoth appears to have waged war during a dormant period, detonating in a single, unimaginable burst of energy. Picture a sleeping volcano that doesn't just wake with a rumble but explodes with enough force to vaporize continents. Then multiply that by a scale where entire galaxies are mere embers in the aftermath. The black hole's jets, typically narrow and focused, must have widened into a tsunami of plasma, carving through intergalactic gas like a blowtorch through butter. The energy released, equivalent to billions of supernovas detonating simultaneously, a flash so bright it would have outshone the entire universe for a fraction of a second had anyone been there to witness it. What makes this explosion so baffling isn't just its scale but its timing. Black holes are known for episodic outburst cycles of feeding and eruption that leave cavities in their wake. But Ophiuchus's cavity is too perfectly spherical, too symmetrical to be the result of multiple small bursts. This was a single, coordinated detonation, the cosmic equivalent of a bomb going off in slow motion over millions of years. Some researchers speculate the black hole might have swallowed something extraordinarily dense, like a wayward star cluster or a rogue black hole, triggering an energy release beyond anything in our models. Others wonder if we're seeing evidence of a new class of eruption, a rare universe-shaking event that occurs only when specific, catastrophic conditions align. Yet the most haunting question isn't what caused the blast, it's what came next. For all its fury, the eruption left almost no visible trace. The cavity was discovered not by telescopes capturing light, but by radio observatories mapping the faintest whispers of energy lingering in the gas. It's as if the universe itself tried to erase the evidence, leaving behind only a ghostly imprint in the cosmic background. That invisibility hints at an unsettling truth. If an explosion this massive could go unnoticed for so long, what other titanic events might we be missing? The Ophiuchus eruption isn't just a record breaker, it's a warning. Somewhere out there, another black hole might be winding up for its own cataclysmic strike, and we might not see it coming until the void starts to bleed. Deep in the cosmic shadows, where telescopes see nothing, the true scaffolding of the universe lies hidden threads of dark matter so vast they weave galaxies into a single interconnected web. These are the cosmic filaments, highways of invisible matter stretching hundreds of millions of light years, binding galaxy clusters together in a gravitational embrace. But how do you map something you can't see? The answer lies in one of nature's most brilliant tricks, the way massive objects bend the very fabric of space itself. When light from distant galaxies travels toward Earth, it doesn't move in a straight line. Any massive object, a galaxy cluster, a black hole, or those hidden dark matter filaments warp spacetime around it, acting like a lens that distorts and magnifies the light behind it. This phenomenon, called gravitational lensing, lets astronomers trace the invisible. Picture holding a magnifying glass over a newspaper, the words beneath distort, revealing the lens's shape. In space, when background galaxies appear stretched into arcs or smeared into strange, repeating patterns, it's a telltale sign of dark matter's hidden hand. Recent breakthroughs have turned this cosmic sleuthing into an art form. By analyzing distortions in thousands of galaxies, scientists reconstruct the dark matter filaments connecting clusters like beads on a string. The Dark Energy Survey, for example, spent years mapping subtle lensing effects across 1/8 of the sky, uncovering a sprawling network of these ethereal tendrils. Some filaments stretch so far they could bridge the distance between our Milky Way and Andromeda 20 times over. Yet they contain no stars, no gas, nothing but the enigmatic pull of dark matter. But here's the spine-chilling part. These filaments aren't passive threads. They're dynamic rivers of gravity, channeling galaxies toward dense clusters in a slow-motion cosmic migration. Simulations show dark matter flows along these filaments like water through a pipeline, dragging galaxies along for the ride. Without them, galaxy clusters would never have formed. They're the universe's delivery system, funneling matter into the hubs where galaxies congregate. Yet for all their importance, dark matter filaments remain maddeningly elusive. Unlike galaxy clusters which light up the skies, filaments reveal themselves only through their subtlest influences, a slight warp in a distant galaxy's shape, a statistical anomaly in the cosmic microwave background. Some researchers compare it to mapping a city's power grid by watching how streetlights flicker. But with every new survey, every deeper scan of the lensing sky, we're sketching the outlines of this shadow architecture, one distortion at a time. And perhaps that's the most humbling revelation of all. The universe we see, the glittering galaxies, the radiant clusters, is just the icing on an invisible cake. The real structure, the true framework of existence, is woven from stuff we'll never see directly. Yet through gravity's gentle fingerprints, we're learning to read the hidden blueprint of the cosmos, tracing the dark threads that stitch the universe together. Nearly 14 billion years ago, the universe was a seething cauldron of plasma so hot and dense that sound waves could ripple through it like vibrations through molten metal. When the cosmos finally cooled enough for atoms to form, those waves froze in place, leaving behind ghostly imprints we now call baryon acoustic oscillations. Today, these colossal ripples serve as the universe's measuring tape, perfectly spaced markers stretching 500 million light-years apart, etched into the cosmic web like a celestial barcode. Imagine throwing a stone into a still pond and watching the ripples expand outward. In the early universe, pressure waves from the Big Bang did something similar, pushing matter into spherical shells before abruptly stopping when light and matter decoupled. The result, a universe with a built-in pattern concentric rings of clustered galaxies separated by predictable distances. What makes these oscillations so invaluable is their perfection as standard rulers. Unlike man-made tools that warp or wear over time, baryon acoustic oscillations remain pristine, their scale unaffected by billions of years of cosmic evolution. Astronomers first detected these fingerprints in 2005, using galaxy surveys to map the subtle overdensities where matter clumped along those ancient sound wave shells. The spacing matched predictions flawlessly, like discovering a fossilized echo of the universe's first scream. But the real breakthrough came when scientists realized these oscillations could track dark energy's influence. By measuring how the apparent spacing of these ripples changes across different eras, researchers can calculate how fast the universe has expanded over time. It's like finding mile markers along a highway and noticing they're farther apart than they should be, proof that the road itself is stretching faster than expected. What's astonishing is how these oscillations bridge extremes. They connect the subatomic quantum jitters of the infant universe to the macroscopic structure of galaxy clusters today. The same physics that governed sound waves in primordial plasma now sculpts the distribution of superclusters and voids. Even more remarkable, the oscillation scale depends on the speed of sound in that early plasma, a value dictated by fundamental constants. This means baryon acoustic oscillations don't just measure cosmic expansion, they test whether the laws of physics themselves have changed over time. Yet for all their precision, these oscillations carry mysteries. Some studies suggest slight deviations in their spacing at larger distances, hints that dark energy's strength might vary across cosmic epochs. Others use them to probe the universe's curvature, searching for evidence that space isn't flat but subtly warped on the grandest scales. Every new galaxy survey, from the Sloan Digital Sky Survey to the upcoming Euclid mission, sharpens our view of these frozen waves, turning them into ever more sensitive probes of the cosmos's secrets. In the end, baryon acoustic oscillations are more than relics, they're a dialogue, a conversation between the universe's fiery birth and its icy fate, written in the language of clustered galaxies and empty voids. And as we decode their message, we're not just measuring space, we're listening to the echoes of time itself. The universe as we know it is on borrowed time. The same dark energy accelerating cosmic expansion today will someday tear apart the very structures we've marveled at, not with violence, but with an inexorable, silent pull. Picture the cosmic web not as a static sculpture, but as a living tapestry slowly unraveling thread by thread. Over the next 100 billion years, galaxy clusters like Coma and Perseus will become isolated islands, their filamentary bridges stretched thin by the universe's swelling emptiness. Neighboring superclusters, now separated by mere hundreds of millions of light years, will drift so far apart, their light will never cross the growing void between them. The Hercules-Corona Borealis Great Wall. It'll still exist, but its galaxies will redshift into invisibility, their light stretched beyond detection by the relentless expansion of space itself. But the unraveling won't happen uniformly. Gravity's grip is strongest where matter is densest, meaning the cores of galaxy clusters will resist separation longest. Places like the Shapley Supercluster, with its incredible concentration of mass, might hold together for 1 trillion years, growing even denser as they cannibalize nearby galaxies. Yet even these fortresses will eventually succumb. As dark energy's influence grows, it will overpower gravity's pull on all but the smallest scales. Galactic mergers, the collisions that built today's megastructures, will cease entirely. The universe's construction phase will be over, replaced by an era of irreversible fragmentation. The most haunting transformation will occur in the voids. Already sparse regions like the Bootes void will expand faster than the universe's average, becoming truly barren. Gas too diffused to collapse into new stars will thin further, leaving future civilizations, if any exist, with skies devoid of galactic neighbors. Distant galaxies won't just appear to move away. Their light will redshift into oblivion, erasing all evidence of the cosmic web from observable reality. The CMB's whisper will fade to silence as its wavelengths stretch beyond detection. The universe won't just be expanding, it'll be deleting its own history. Yet amid this dissolution, a paradox emerges. While most structures are torn apart, the tightest gravitational bonds will endure. The Milky Way and Andromeda, destined to merge in 5 billion years, will form a single elliptical galaxy, one of the last islands in an ever-darkening sea. Local group galaxies bound to them will remain visible, but everything beyond will vanish into the void. Future astronomers might deduce the universe is expanding from these few nearby redshifts, but the grand tapestry of walls and filaments we see today, it'll be lost to time, leaving them with no clues that cosmic structures once spanned billions of light years. This slow-motion erasure raises profound questions. If dark energy's strength changes over time, a possibility some theories suggest the timeline could accelerate or stall. A hypothetical Big Rip scenario where dark energy intensifies enough to shred galaxies and even atoms remains unlikely but not impossible. More probable is a gradual heat death where structures fade but persist in isolation until the last stars burn out. Either way, the epoch of cosmic architecture, this brief window where gravity's artistry is visible across the heavens, is fleeting by universal standards. We're living in the golden age of cosmic structure, privileged to witness the universe's grand design before the curtains close. And perhaps that's the ultimate lesson these megastructures teach. Their scale humbles us not just spatially but temporally. They remind us that the universe is a dynamic, evolving entity, one that builds and destroys on timelines we can barely fathom. The great walls and voids we map today aren't permanent landmarks, but transient features in a story spanning trillions of years. Our ability to see them at all is a cosmic coincidence, a fleeting alignment of time and perspective that future civilizations might never share. So while we still can, we keep searching, measuring, marveling, documenting the universe's grandeur before the tide of expansion carries it all beyond the horizon of perception. Every structure we've explored, from the Hercules-Corona Borealis Great Wall to the Saraswati Supercluster, exists within a fragile bubble of perception, the observable universe. This sphere, stretching 93 billion light-years across, represents the ultimate horizon of human knowledge, the farthest light that's had time to reach us since the Big Bang. But here's the unsettling truth lurking behind every cosmic map we've ever made. These titanic walls and voids might be mere neighborhood landmarks in a universe so vast, our entire observable volume could be smaller than a grain of sand on an endless beach. The irony is crushing. Just as we've begun decoding the cosmic web's architecture, tracing filaments that span billions of light years, we're forced to confront the possibility that these are trivial patterns compared to what lies beyond. Cosmologists call this the end of greatness, the scale at which the universe should theoretically become smooth and uniform. Yet every time our telescopes improve, they reveal larger structures, as if the cosmos is taunting us with its refusal to conform. The Great Walls, the giant arc, even the South Pole Wall, they all flirt with the upper limits of that observable sphere, their edges vanishing into the darkness as if hinting at grander designs just out of reach. What makes this boundary so profound isn't just its physical limit, it's how it warps our understanding of reality. Light from regions beyond the observable universe will never reach Earth, not because it doesn't exist, but because space itself is expanding faster than light can traverse it. This means there are galaxies, superclusters, perhaps even entire cosmic webs whose light is forever lost to us, racing away in the darkness like ships swallowed by fog. Some theories suggest these hidden regions could host structures dwarfing anything we've documented, walls of galaxies stretching tens of billions of light years, or voids so deep they make Bootes look like a puddle. The real tease lies in the cosmic microwave background, those faint temperature fluctuations, the same ones that seeded today's superclusters, hint at structures larger than our observable horizon, frozen in the instant after the Big Bang. It's as if we're deciphering shadows on a cave wall, knowing the objects casting them lie forever out of view. Simulations exacerbate the itch. When cosmologists model volumes much larger than our observable universe, they find intricate patterns repeating on scales that humble even the most ambitious galactic surveys. Yet for all its frustration, this horizon holds a strange gift. The very fact that we can conceptualize an outside, that we can use mathematics and physics to speculate about realms no telescope will ever see, speaks to the human mind's audacity. We're prisoners of our tiny bubble, but through science, we've learned to read the prison walls like a manifesto, tracing the strokes of a universe vaster than our tools can capture. Those great structures we marvel at, they're not just destinations, they're signposts pointing toward mysteries we're only beginning to name. And in that unknowing, there's a peculiar kind of freedom, the freedom to imagine, to question, and to keep reaching, even when the universe insists some answers will always lie in the dark. From galaxies spanning walls to cosmic voids deeper than imagination, the universe's largest structures have shattered every assumption we once held about scale, order, and the limits of reality. These 30 facts aren't just a catalogue of celestial giants, they're a testament to how little we truly understand the cosmos. The Hercules-Corona Borealis Great Wall defies the very laws of time and gravity. The Bootes void whispers of emptiness so profound it redefines isolation, and dark flow tugs at galaxies with the gravity of something beyond our horizon, hinting that the observable universe might be just the first chapter in a story too vast to comprehend. What's most humbling isn't just the size of these structures, it's the way they force us to rewrite the rules. The cosmic web, woven from dark matter and threaded with galaxies, behaves less like a random scattering and more like a meticulously planned blueprint. Superclusters like Laniakea and Shapley don't just exist, they dominate, bending the motion of everything around them with gravitational might that spans hundreds of millions of years. And let's not forget the Phoenix Cluster's stormy heart, where black holes orchestrate weather systems on scales larger than entire galaxies. Every discovery peels back another layer, revealing a universe that's stranger, more intricate, and more defiant of our models than we ever dared to predict. Yet for all we've mapped, these giants are likely just the beginning. Imagine what lies beyond the reach of our telescopes, structures so colossal they make the great walls we know seem like mere brushstrokes on an infinite canvas. Could there be filaments stretching tens of billions of light years, or voids so vast they dwarf even the Eridanus supervoid? And what if the anomalies we've spotted, the cold spots, the unexplained flows, are glimpses of physics beyond our current theories, or even bridges to other universes? The unsettling truth is this: we're only seeing the fraction of reality that's had time to send us its light. So here's the invitation, not just to marvel, but to wonder. Which of these cosmic titans left you awestruck? Was it Alcyone, the galaxy so large it rewrote the definition of size, the haunting symmetry of the giant arc, or the way the South Pole wall hid in plain sight behind our own Milky Way? Drop your thoughts in the comments, because this conversation doesn't end here. Every time we point a telescope skyward, the universe reminds us that the greatest discoveries aren't just about finding answers, they're about learning how much more there is to ask. And who knows, the next cosmic record breaker might already be out there, waiting for someone bold enough to look.